Let's talk about a very important aspect of chemistry, which is the topic known as stoichiometry. Now, from what I've been able to observe for quite some time, a lot of students in chemistry find stoichiometry as the most difficult topic in chemistry. But the reality is that stoichiometry is perhaps the simplest topic, one of the simplest topics in chemistry. So it just depends on your ability to understand the fundamental principles that govern stoichiometry, which I will review throughout the duration of this particular class. So please try as much as possible to listen attentively, and I guarantee that by the end of this class you should be able to solve every single question you can encounter under stoichiometry. Now, this is the outline we'll be using. Give an introduction to stoichiometry. We'll talk about the stoichiometry of composition, essentially your mole concept. We'll talk about the stoichiometry of reactions, percentage purity, stoichiometry of neutralization, and we'll end the class with limiting and excess reagents. So to understand what stoichiometry is talking about, we have to begin by breaking down the word stoichiometry into two parts. So stoichiometry actually comes from a Greek word, two Greek words actually. So if we are to break down the word stoichiometry, we'll get two parts. We have stoichion and we have metron. Stoichion is from the word that means element. Metron is from the word that means measure. So stoichiometry can literally be defined as the measurement of the amount of elements. But if we were to give a much more comprehensive definition of stoichiometry, I would say that stoichiometry is the aspect of chemistry that deals with the amount or the measurement of elements in a sample, as well as the amount of reactants and products that participate in the chemical reaction. So there are two aspects of stoichiometry which we shall discuss. We said that stoichiometry involves the measurement of the amount of elements in a sample, and it also involves the amount of measurement of the reactants and products that are involved in the chemical reaction. So based on that definition now, we can now divide stoichiometry into two aspects. We could have stoichiometry of composition, where we are talking about the measurement of the amount of elements in the sample. And we could also have stoichiometry of reaction, where we are concerned with the amount of reactants and products that participate in the chemical reaction. So for the duration of this class, for the sake of this class, we'll split stoichiometry into two parts. The two parts being stoichiometry of composition and stoichiometry of reaction. So stoichiometry of composition, we'll be talking about your mole concept. So the basic idea behind stoichiometry of composition is essentially your mole concept. And the reason why I had to split stoichiometry into two parts is because mole concept and the typical stoichiometry that we know, they are intertwined with each other. So we have to split it into two parts and discuss mole concept separately. So when we are done, we can apply the knowledge of mole concept to stoichiometry of reaction. So we have two important aspects: stoichiometry of composition, where we'll talk about mole, and we have stoichiometry of reactions, where we'll talk about the measurement of the amount of reactants and products. So let's begin. Let's begin by talking about stoichiometry of composition, basically mole concept. Now think about it this way. If your mom wants you to get eggs for her, she can tell you the amount of eggs she wants in two different ways. She can tell you, please go into the storeroom and get me 12 eggs. And almost immediately you go into the storeroom and you emerge with 12 eggs. No issues. Now she can also tell you, please go into the storeroom and get me a dozen eggs. At the same time, you go into the storeroom, and what you will come out with is the same 12 eggs. But she didn't tell you go into the storeroom and give me 12 eggs. No, she said go into the storeroom and give me a dozen eggs. But you went in and you came out with 12 eggs. That simply means that a dozen is simply another way of representing 12 eggs. A dozen of eggs is simply another way of representing 12 eggs. Likewise, a crate of eggs contains about 30 eggs. So she can still tell you go into the storeroom and get me 30 eggs, and you go in and you emerge with 30 eggs. She can also tell you go into the storeroom and get me a crate of eggs and you go into the storeroom, you come out with exact same 30 eggs. So it simply means that a crate of eggs is simply another way of representing 30 eggs. So a dozen represents 12 eggs, a crate of eggs represents 30 eggs. So in other words, we can apply the same knowledge back to chemistry. So instead of saying, like in this example we gave, instead of saying 12 eggs, I can simply say a dozen. Instead of saying 30 eggs, I can simply say a crate. So in other words, a dozen of eggs simply refers to the amount of eggs that contain 12 eggs. Likewise, a crate of eggs represents the amount of eggs that contain 30 eggs. In chemistry, we do something similar because we are working with small, tiny particles, atoms, molecules, and ions. So we need a way we can simplify the amount of these particles, the amount of these elements, the amount of these atoms, molecules, and ions that we generally work with. So instead of saying in this case 30 eggs, I can say a crate of egg. So in chemistry, we do something similar by inventing a term. That term is what we refer to as mole, where we say that a dozen of eggs represent the amount of eggs that contain 12 eggs, and a crate of eggs represent the amount of eggs that contain 30 eggs. Mole represents the amount of a substance that contains 6.02 times 10 raised to power 23 particles. So whenever I hear a dozen eggs, what comes to my mind is 12 eggs. Whenever I hear a crate of eggs, we say it is the amount of eggs that contain 30 eggs. So whenever I hear mole, it simply means what comes to my mind should be 6.02 times 10 raised to 23. So mole simply represents the amount of a substance that contains 6.02 times 10 raised to 23 particles. Now this 6.02 times 10 raised to 23 is actually a constant known as Avogadro's constant or Avogadro's number. Very simple. So mole is simply a way we can use in chemistry to simplify the amount of elementary entities like atoms, like molecules and ions, or to measure the amount of elements that we have in a sample, which is the basic idea behind stoichiometry of composition. So one more time, we said mole is the amount of a substance that contains 6.02 times 10 raised to the power 23 particles of that same substance. What that means is that I can say that 1 mole of hydrogen, 1 mole of hydrogen atom, the number of atoms that it will contain will be 6.02 times 10 raised to the power 23 atoms. I can as well say that 1 mole of hydrogen molecule, the number of molecules that it would contain would be 6.02 times 10 raised to the power 23 molecules. So make sure that sticks. So mole, like I said, represents the amount of a substance that contains 6.02 times 10 raised to the power 23 of that same substance. Easy. Now, they can also ask you, the same 1 mole of hydrogen molecule, the same 1 mole of hydrogen molecule, how many atoms does it contain? The same 1 mole of hydrogen molecule, how many atoms does it contain? Will it still be 6.02 times 10 raised to the power 23? No. You have to now understand this time around that 1 mole of hydrogen molecule is simply made up of 2 moles of hydrogen atom, where each 1 mole is having 6.02 times 10 raised to the power 23 atoms. 6.02 times 10 raised to the power 23 atoms. So remember where we came from? 1 mole of hydrogen atom contains 6.02 times 10 raised to the power 23 atoms. 1 mole of hydrogen molecule contains 6.02 times 10 raised to the power 23 molecules. But this time around, 1 mole of hydrogen molecule, how many atoms would it contain? We said that the same 1 mole of hydrogen molecule is actually made up of 2 moles of hydrogen atom, where each one of them has 6.02 times 10 raised to the power 23 atoms. So therefore, I can simply say that 1 mole of hydrogen molecule will contain 2 times 6.02 times 10 raised to the power 23 atoms. Very simple. I hope you understand. I hope that makes perfect sense. Now, let's continue. Now remember we gave a definition for mole as the amount of a substance that contains 6.02 times 10 raised to the power 23 particles of that same substance. But mole goes beyond just telling us the amount of particles that are present in the substance. Mole can also tell us the mass of elements that is present in a sample. Mole can also go on by telling us the concentration of elements that are present in a solution. Mole can also go on to tell us the volume of a gas that is present in the container at STP. So mole goes just beyond, it goes far beyond just telling us the number of particles, elementary entities like atoms and molecules and ions that are present in a substance. Now, since we just said that mole can be used to describe not just the number of particles, but also goes beyond that, we can therefore study mole by dividing it into several cases. So this would be case 1, this would be case 2. So case 1 would be mole based on mass. Case 2 would be mole based on number of elementary entities. Based on number of particles. So let's see. Now, based on mass, mole would be equals to mass over molar mass. This will be equal, n will be equals to small m over big M. So based on mass, remember we said that mole can also describe the mass of a substance in a sample, mass of an element, or a compound in a sample. So what becomes the relationship between the mole of that substance and the mass of that substance? That's what we have on the board. Mole equals mass over molar mass. Now we just introduced a new term, molar mass. What is this molar mass that we are talking about? Now, to better describe molar mass, let's make our mole equals to 1. Let n equals 1. So when our mole is equals to 1, fix it into this equation. We have 1 equals mass over molar mass, cross multiply. What do I have? At the end of the day, I will have that my mole is equals to my mass. This becomes the relationship I have. What does this mean? This means that molar mass is simply the mass of 1 mole of a substance. So for every 1 mole of a substance, its mass is actually the molar mass. What do I mean by that? We said that for every 1 mole of oxygen, for instance, let's use oxygen. So for every 1 mole of oxygen, molecule, we say the number of particles or the number of molecules that would be present in every 1 mole of oxygen molecule would be 6.02 times 10 raised to the power 23 molecules. Likewise, for the same 1 mole of oxygen molecule, its mass, for the same 1 mole of oxygen molecule, its mass in grams would be 32 grams. We say 32 grams per mole, meaning that it is 32 grams for every 1 mole, or every 1 mole of oxygen molecule would actually weigh 32 grams. So molar mass, by extension, we said, is the mass of 1 mole of a substance. So in terms of number of elementary entities, each 1 mole would have 6.02 times 10 raised to 23, and each 1 mole would weigh its molar mass. So for example, 1 mole of oxygen molecule would have 6.02 times 10 raised to the power 23 oxygen molecules, and at the same time would weigh 32 grams. Easy. But how do we determine this molar mass of element or molar mass of compound? It is very easy. So let compound equals AXBYCZ. So let the compound be AXBYCZ. This time around, I want to determine the molar mass of this compound AX, BY, and CZ. What do I do? Very simple. The molar mass of a substance is equal to the RAM of each of the elements in the substance multiplied by the number of atoms present. Simple. I'll run through one more time. We say that it is equals to the RAM of each of the elements present multiplied by the number of atoms present. So meaning that there are X number of A in this compound, Y number of B in this compound, and Z number of C in this compound. So what becomes the molar mass of this compound? The molar mass of this compound would be X, Y, X, Y, Z. So this will be X in bracket RAM of A plus Y in bracket RAM of B plus Z in bracket RAM of C. Very simple. Very easy. Very easy. Very easy. So the molar mass of this compound, I can easily determine it. So let's assume, determine the molar mass of, let's say, we have, let's say, hydrogen, or rather water. Let's use water, for instance. So H2O, meaning that there are 2 atoms of H and 1 atom of oxygen. What becomes the molar mass? The molar mass will simply be equal to, the molar mass will be equal to 2 hydrogen plus 1 oxygen. What is the RAM of hydrogen? The RAM of hydrogen is 1. This will be 2 in bracket 1. Plus what is the RAM of oxygen? The RAM of oxygen is 16. So 2 times 1 gives us 2 plus 16. This gives us 18 grams per mole. That simply means that every 1 mole of water would contain 6.02 times 10 raised to the power 23 atoms of water, and at the same time it would weigh 18 grams. Very easy. Very easy. So the molar mass of a substance is the mass of every 1 mole of that particular substance. So remember, the relationship between the mass of a substance and its mole is that mole equals mass over molar mass. It gives us the answer to whatever question we are asked based on this relationship. Now, this is case 1. Now, we just discovered that there's a relationship between mole and mass, and we just exploited that relationship by saying that mole equals mass over molar mass. Now, at the same time, we can move on to case 2 by exploiting a relationship, this time around not between mole and mass, but between number of elementary entities, which we talked about. So mole based on number of particles. Number of particles. So what would I have? I would simply have mole equals number of particles. The particles can be atoms, there can be molecules, there can be ion, all over Avogadro's constant, which is 6.02 times 10 raised to the power 23. Very easy. So if you are given a question where you are given the number of particles present in the substance and you are asked to determine the mole, this becomes a relationship between mole and number of particles. So mole can also describe the number of particles, which was actually the definition for mole that we gave. This is case 2. Now I can also have case 3. This time around, it is mole based on concentration. Mole based on concentration. So for a substance that is in solution, we can also be asked to determine the mole of that substance, meaning that there should be a relationship between mole and concentration of a substance. What becomes that relationship? We said that mole is equals to concentration of the substance times volume of that substance. Mind you, the volume SI unit is in dm cube. But if it is in cm cube, we have to divide by 1000. So I would have mole equals CV if it's in dm cube, or CV over 1000 if this our volume is in cm cube. Very easy. So if I'm given the concentration of a substance, I'm given the volume of the solution, and I'm asked to calculate for the mole, I can easily use this relationship to determine the mole under that condition. Very easy. This case 3. Case 4, which is the final case we talk about, is mole based on volume at STP. So remember, STP stands for standard temperature and pressure. So mole can also be used to describe the volume of a gas at STP. Remember we said mole can describe concentration of a substance in solution. So mole can also describe the volume of a gas at STP. What becomes the relationship between mole and volume of that gas at STP? We say that mole is equals to the volume of gas all over molar volume. Now remember, we introduced a concept before, which is molar mass, and we said the molar mass is the mass of every 1 mole of a substance. So what about the molar volume? The molar volume becomes the volume of 1 mole of a gas at STP. Very easy. So unlike molar mass, where we have to calculate it, for the molar volume, we don't need to determine the molar volume. It is a constant. So the molar volume is a constant. It has a magnitude of 22.4 dm cube or 22400 cm cube. So every 1 mole of a substance would weigh its molar mass and would contain 6.02 times 10 to the power 23 particles. And at the same time, every 1 mole of a substance, its volume, every 1 mole of a gas to be specific, its volume would be 22.4 dm cube or 22400 cm cube. 1 mole of a gas at STP would occupy this particular volume. So I can say therefore that N should be equals to volume over 22.4 if this volume is in dm cube, or volume if the volume is in cm cube over 22400 cm cube. This becomes the equation, or rather the formula, that can be used to determine the mole. I hope all of this makes sense. So now that we've successfully given the relationship between mole and number of particles, the relationship between mole and volume of gas, the relationship between mole and concentration, and the relationship between mole and mass, we can therefore give a general formula that we link up all of these statements together. So all of these statements, we can link them up together by using a simple general equation. And what becomes that equation? We have mole is equals to mass over molar mass. This same mole is equals to number of particles over Avogadro's constant, 6.02 times 10 raised to the power 23. This same mole is equals to volume over 22.4 or volume over 22400 cm cube. This same mole is equals to CV or CV over 1000 if the volume is in cm cube. Very easy. So the reason why I'm giving this general formula is because of how the questions will come. So there are some questions that will involve us linking 2 different formulas for mole to get our answer to the question. So for example, we can be asked to look for the volume of a gas if its mass is x grams. So determine the volume of x grams of oxygen at STP. So under that condition, I have to link up these 2 volumes because my parameters would contain mass and molar mass and also contains volume. So I can link up either of these formulas and I'll get the answer to the question. I can also be given questions where, based on the parameters, what I have in the question, we have to combine number of particles over Avogadro's constant equals mass over molar mass, or even equals volume over 22.4, or even equals CV over 1000. So that is why this aspect is very important. So I hope all of these things we've discussed makes perfect sense, because you need a proper understanding of stoichiometry of composition before you can finally understand the stoichiometry of reaction. So now that we've talked about stoichiometry of composition, and I believe it makes sense at this point, we can now discuss the stoichiometry of reaction. The stoichiometry of reaction is the second aspect of the definition of stoichiometry, which is the quantitative measurement of the amount of reactant and product that is involved in a chemical reaction. So essentially, in stoichiometry of reaction, we are generally concerned with the reaction, the amount of reactants that react together and the amount of product that are formed from a specific amount of reactants. That is the basic idea behind stoichiometry of reaction. However, we still apply the knowledge of stoichiometry of composition, Mole concept. We still apply the knowledge of Mole concept to the stoichiometry of reactions. Now, to have a good understanding of stoichiometry of reactions, we first of all need to talk about something very important, which is stoichiometric coefficient. So, what is a stoichiometric coefficient, or what are stoichiometric coefficients? Coefficients. Now let us consider a chemical reaction. Let's say a reaction between A plus B to give C plus D. Now, if this is a chemical reaction, usually you will observe that almost every chemical reaction, there are certain numerical values that are attached to each of the components of the reaction. Let's say, for example, we have X, we have Y, we have Z, and we have Q. So the numerical values that are attached to each of the components of a balanced chemical reaction, the numerical values that are attached to each of the components of a balanced chemical reaction, these numerical values are what we refer to as stoichiometric coefficients. So what are stoichiometric coefficients? One more time, we said that there are numerical values that are attached to each of the components of a balanced chemical reaction. And what are their functions? The stoichiometric coefficient tells us two important things. The stoichiometric coefficient tells us the ratio at which the chemical reactants react together and the ratio at which the products are formed. So for example, the stoichiometric coefficient tells me that the ratio at which A will react with B will be in the ratio of X ratio Y. And the ratio at which the products are formed, C, will be in the ratio of Z ratio Q. So that's one thing the stoichiometric coefficient tells us. It gives us an idea of the relationships, or rather of the mole ratios. Let's put it that way: the ratio of the reactants that react and the ratio of the products that are formed. The stoichiometric coefficient also gives us an idea of the amount of the reactant and products that are formed in the chemical reaction, or the amount of reactants that react in the chemical reaction. So the first thing we said was that the stoichiometric coefficient gives us an idea of the ratio at which reactants react and the ratio at which products are formed. But also, it gives us an idea of the amount of the reactants that react and the amount of the products that are formed. So for example, the stoichiometric coefficient tells us that X mole of A will react with Y mole of B, and then we form Z mole of C, and then we form Q mole of D. So the stoichiometric coefficient gives us an idea of the amount of the reactants that react in the chemical reaction and the amount of product that is formed in the reaction. So let's use a standard chemical reaction to illustrate what I'm trying to see. So let us consider the combustion of hydrogen in excess air. So we have a reaction. This is 2H2 gas plus O2 gas to give 2H2O. So this is a reaction between hydrogen and oxygen to form water. Now these numerical values that are attached to each of the components in this reaction, that is what we refer to as the stoichiometric coefficient. And what do the stoichiometric coefficients tell us? They give us an idea of the amount of the reactants and products that are present in this reaction, the amount of reactants and the amount of product. Now the amount of the reactant can be expressed in mole. It can be and from our previous encounter with mole, we know that we can also express it in terms of volume, in terms of mass, in terms of number of elementary entities, and so on. So I can say that the stoichiometric coefficient here is 2:1:2. It gives us an idea of the ratio at which they react. It also gives us an idea of the amount of the reactant in this reaction and the amount of the product formed in this reaction. So that amount, like I said, can be in mole. So I can say that 2 mole of hydrogen we need to react with 1 mole of oxygen to form 2 moles of water. I can also say this same mole, from what we said under based on composition, this same mole can also be expressed in terms of mass. So the stoichiometric coefficient can also give us an idea of the mass of the reactants and the mass of the product present in the reaction. And remember, we said that the mass of 1 mole of a substance is equivalent to the molar mass. So this is stoichiometric coefficient giving us in terms of mole. It can also be expressed in terms of mass. So this becomes 2 in bracket. This will be 2 grams of hydrogen molecule. Remember, 1 mole, the mass of every 1 mole of a substance is the molar mass. So this will be 2 in bracket, 2 grams of hydrogen molecule. We always react with 1 bracket. This will be 32 grams of oxygen molecule. And when they react, they will always form 2 in bracket, 18 grams of water. In case you are wondering where am I getting the values from, I'm getting the values from their molar mass, because we just said that the mass of every 1 mole of a substance is equivalent to the molar mass. So I'm expressing this mole in terms of the molar mass. It should make sense if you understand what we discussed under stoichiometry of composition. Now, after expressing it in terms of gram, the stoichiometric coefficient can also give us an idea of the number of particles that are present in this reaction, number of particles of hydrogen that are involved in this reaction, number of particles of oxygen that are involved in the reaction, and number of particles of water that are formed in this particular reaction. So therefore, in terms of number of particles, I can simply say that 2 in bracket 6.02 times 10 raised to the power 23 molecules of hydrogen. We always react with 1 in bracket 6.02 times 10 raised to the power 23 molecules of oxygen to form 2 in bracket 6.02 times 10 raised to the power 23 molecules of water. Remember that I'm doing this. Why? Because I have a basic understanding of mole concept, where I know that the mole can be expressed in terms of mass. It can also be expressed in terms of number of particles. Now, I can also use the stoichiometric coefficient to express the volume of the substance if it is a gas. In this case, we said that all of them are gases. So in this case, I can also use the stoichiometric coefficient to give me an idea of the volume of the reactants involved and the volume of the product that is formed. So in terms of volume at STP, I would have 2 in bracket 22.4 dm³ of hydrogen gas at STP would always react with 2 in bracket 22.4 dm³ of oxygen gas at STP to form 2 bracket 22.4 dm³ of water at STP. So the stoichiometric coefficient is actually the reason why I'm able to do all of these things. And like I said, it is an application of our stoichiometry of composition. Now, all of these things are important. Why? Because in stoichiometry, or based on what we have done so far, you have now seen that there's always a relationship between the reactant, and also there's always a relationship between the product. So in stoichiometry questions, they'll give us two things. One of them is the known, which is the known amount. Then they will ask us to look for something. So what they're asking us to look for becomes the unknown. So the known or the unknown can either be the product or it can also be the reactant as well. So essentially, the most important rule is stoichiometry. The most important rule in stoichiometry is to establish a relationship between what you have and what you are looking for, to establish a relationship between the known and the unknown. Once you can establish that relationship, you identify which type of relationship it will be. So will it be a mass-to-mass relationship? Will it be the mole-to-mole relationship? Will it be a volume-to-volume relationship? And so on. So what we are going to be discussing is the relationship between each of the reactants or product, between the known and the unknown, in terms of their amount. Now, like we've said so far, that amount can be expressed in terms of mass, in terms of mole, in terms of volume. So that can give us several types of relationship. So the first relationship we'll explore is the mole-to-mole relationship. So the mole-to-mole relationship is a stoichiometric relationship where the known and the unknown are both expressed in terms of mole. So the known and the unknown are both expressed in terms of mole. So they are asking me to look for this, or rather, they give me this, the known, and this is unknown. Sorry. They gave me the known in terms of mole, and they are also asking me to look for the unknown also in terms of mole. So how do I approach that question? Very simple. Remember, we said that the most important rule in stoichiometry is to establish a relationship between what you have and what you are looking for, or between the known and the unknown. So I will use one question, and that question, I will use one question for all of the relationships, and I will just be changing a little bit of parameters of that question. And the reason I'm going to do that is that I want to show you that all of these relationships, they are kind of linked together, and they are also very easy to solve. So for example, let's take a question. It said determine, let's see how we'll solve this question. Determine the amount in mole of hydrogen needed needed for needed to form, let's put it this way, needed to form 3 grams, or rather 3 moles of water. So it is a very simple question. We are asked to determine the amount in mole of hydrogen needed to form 3 moles of water. So the basic reaction would be 2H2 plus O2 to give 2H2O. Very simple, straightforward reaction. Now from the stoichiometric coefficient, remember we said the stoichiometric coefficient tells us that 2 ratio 1 ratio 2. So the ratio at which hydrogen and oxygen will react will be 2 ratio 1, and the ratio at which water will be formed will also be 2 ratio 1 as well. So how then do we solve this question? We said establish a relationship between what you have and what you're looking for, between the known and the unknown. So what is my known? Determine the amount. That is my unknown, the amount of hydrogen. So hydrogen becomes my unknown, needed to form 3 moles of water. So water becomes my known. So this is my unknown. This becomes my known. So let's put it one way. This is my known. My known is 3 moles of H2O. My unknown, I don't know. So establish that relationship. So in this reaction, my relationship will be between hydrogen and water. So I would say 2 mole, this is 2H2 to 2H2O. So from what we have, based on stoichiometric coefficient, we know that for every balanced chemical reaction, 2 moles of hydrogen will always react with 2 moles of water. So every time, we always form 2 moles of water. So every time hydrogen is to react with oxygen, it will always form, every 2 mole of hydrogen will always form 2 mole of water. So therefore, what if we don't have 2 moles of water being formed? What is this? What if this time around we have 3 moles of water being formed? What would be the amount of hydrogen X that would react with oxygen to form these 3 moles of water? Very easy. We'll say make X subject, cross multiply, and make X subject. We have 2 times 3 all over 2. So the answer becomes 2 mole. 2 moles of what? 2 moles of hydrogen molecule. So this means that 3 moles rather. This means that 2 moles of hydrogen gas will always form 2 moles of water. So therefore, 3 moles of water will be formed from 3 moles of hydrogen gas. Very simple. This is the basic idea behind mole to mole relationship. Now let's take the next relationship, which is the mass to mass relationship. So the mass to mass relationship is the stoichiometric relationship in which the known and the unknown are expressed in terms of grams or in terms of mass. So we'll use a similar question, and I'll show you what I'm trying to talk about. So we have the question determine the mass of oxygen needed for the complete combustion of 8 grams of hydrogen. So let's bring out the parameters of this question. What is the mass of the unknown? Mass of the unknown is what they're asking us to look for. We don't know. But do we know the mass of the known? Yes. Mass of the known, they gave us in the question as 8 grams. 8 grams of what? 8 grams of hydrogen. So very easy. Write the equation for the combustion of hydrogen. I have 2H2 plus O2 to give 2H2O. So the stoichiometric coefficient tells us that 2:1:2. So the ratio at which hydrogen will react with oxygen to form water will be in 2:1. Very easy. Then we said, what do I do at this point? We said, create the relationship between what you have and what you are looking for, between the known and the unknown. So my relationship becomes between 2H2 to O2. Now, based on the stoichiometric coefficient, I'm aware that 2 moles of hydrogen will always react with 2 moles of oxygen. Rather, we always react with 1 mole of oxygen. But as at this point, I'm not concerned with moles because this is a mass-to-mass relationship. Instead, what I'm concerned with is their moles, is their mass. So therefore, I will express this mole in terms of mass. From what we have said, from stoichiometry of composition, it should be easy. This becomes 2 in brackets 2 grams of hydrogen. We always react with 1 in bracket 32 grams of oxygen. So every 4 grams of hydrogen, we always react with 32 grams of oxygen. So what now happens when I don't have 4 grams of hydrogen? What happens when I have 8 grams of hydrogen instead? So 8 grams of hydrogen will give us X. So what becomes X? X becomes equal to 8 times 32 all over 2 times 2 grams. This gives us the value for the amount of oxygen that will be needed to burn exactly 8 grams of hydrogen. So it is very, very easy. This is the mass-to-mass relationship that we are referring to. So if you understand mole-to-mole relationship, you understand mass-to-mass relationship, we can apply the same knowledge to volume-to-volume relationship. It is all linked together. They are all linked together and they are all very simple. So let's consider volume-to-volume relationship. So for volume-to-volume relationship, it is simply a stoichiometric relationship where the mass of the substance, or rather the amount of the substance given, is expressed in terms of volumes at STP. So the known and the unknown, they are expressed in terms of volume. So we use a similar question. This time around, it will be determine the volume of oxygen needed for the complete combustion of 4 dm cube of hydrogen. So same question, I just changed the parameters a little bit. So write the equation for the combustion of hydrogen. This is 2H2 plus O2 to give 2H2O. Stoichiometric coefficient 2:1:2. And then we establish the relationship between the known and the unknown. So determine the volume. Our volume of unknown is what they're asking us to look for. Needed for the complete combustion of 4 dm cube of hydrogen. So my volume of known becomes 4 dm cube. 4 dm cube of what? Hydrogen. So I can simply solve. Create the relationship between the known and the unknown. It becomes between 2H2 to O2. So I can say that every 2 mole of this, we always react with 1 mole of oxygen. But like we said before, this is not a mole-to-mole relationship. It is actually a volume-to-volume relationship. So I will express this mole in terms of volume. What would it become? This becomes 2 in bracket 22.4 dm cube, because every 1 mole has a volume of 22.4 dm cube. We always react with 1 in bracket 22.4 dm cube of oxygen. to form water. So therefore, 4 dm cube of hydrogen, what will be the amount of oxygen that it will need for reaction? We don't know. Let's call it x. So make x subject, cross multiply, make x subject. What becomes x? X becomes equals to 4 times 22.4 all over 2 times 22.4. So this 22.4 cancels out. My final answer becomes equals to 2 dm cube. So it is all very easy. It is all very simple, provided you know what you are doing. Now, I can also take another relationship, which is mole to mass relationship. I'll still use the same question, but this time around, determine, remember it is a mole to mass relationship, so the known and the unknown that express both in mole and also in mass, moles to mass relationship. So I'll use the same question this time around, determine the mole of oxygen needed for the complete combustion of 4 grams of hydrogen. So it is still a mole to mass relationship. So this becomes mole of the unknown. Mole of the unknown is what we are looking for, but they gave us mass of the known. Mass of the known they gave us as 4 grams. So what do we do as at this point? We do the same thing we have been doing so far, create the relationship between what you have and what you are looking for. It becomes between hydrogen and oxygen. Same thing, same principle. So this becomes every 2 mole of hydrogen we always react with 1 mole of oxygen. But this is not a mole to mole relationship. This is actually a mole to mass relationship. This side, what becomes our unknown? Our unknown was expressed in terms of mole, and our unknown is oxygen. So this is mole, while our known is expressed in terms of mass. So this is a mass to mole relationship. So it means that on this side, I will express the mole in terms of grams, while on this side, I will express it just in terms of mole. Very easy. So I will simply say that every 2 grams of hydrogen, we always react with 1 mole of oxygen. So therefore, what happens when I don't have 2 in bracket? What happens when I have 4 grams of hydrogen? What will be the amount of oxygen you need for reaction? X. Very easy. What becomes x? X becomes equals to 4 times 1 all over 2 times 2, which will just equals 1 mole. Very easy. So 4 grams of hydrogen. 4 grams of hydrogen, we always need 1 mole of oxygen for reaction. This is the mole to mass relationship. I can also have a mass to volume relationship. So I can have different types of relationships. Whether you have a basic understanding of what we have done so far, you should be able to solve questions based on any type of relationship. So if I'm having a mass to volume relationship, so I can still tweak this question a little bit. It will be determine the mass of oxygen needed for the complete combustion of 4 dm cube of hydrogen. So determine the mass of oxygen. So our unknown is the mass needed for the complete combustion of our known is 4 dm cube of hydrogen. So same thing we have been doing so far. Our relationship becomes between 2H2 to O2. Remember that our unknown is oxygen, and they are asking us to look for the mass. So this side will be mass, and our known is hydrogen. They gave us the volume, so this side would be volume. So this is a mass to volume relationship, meaning that on this side we express the mole in terms of volume, while on this side we express the mole in terms of grams. So naturally we were supposed to say that 2 mole of this, we always react with 1 mole of oxygen, but this is not a mole to mole relationship. So here becomes 2 in bracket 22.4 dm cube of hydrogen will always react with, here we must express the mole in terms of mass. This becomes 32 grams of oxygen. So therefore 4 dm cube of hydrogen, what will be the mass of oxygen that it will need for reaction? X. Make x subject. What would I have? Would have x equals to 4 times 32 all over 2 times 22. This gives us the value of the mass of oxygen that will be needed to completely burn 4 dm cube of hydrogen. So as at this point, I believe you should be able to solve any question you can find, create any relationships that will be demanded based on what we have done so far. Now, we can now talk about some applications of stoichiometry, which is percentage purity, stoichiometry of neutralization, and finally limiting reagent. Although limiting reagent will be a separate video on its own. So for the rest of this video, our main focus will be percentage purity and also stoichiometry of neutralization. Stoichiometry of neutralization is actually an application of stoichiometry in titration. So remember your titration, neutralizing an acid with a base. So let's say HX plus, let's say BOH to represent the base. What would I form? I'll form BX plus H2O. An acid will react with base to form salt and water. Let's give each of them stoichiometric coefficient. Let's say this is M, this is P, this is Q, and this is R, represent the moles of the acid and the moles of base. Now the relationship between the amount of acid and the amount of base that is involved in this reaction will determine the amount of product that will be formed in this particular reaction. So the relationship between the amount of the acid and the amount of the base present in the reaction can be given by a simple formula. This is CAVA over CBVB is equals to Na over Nb. What is your Ca? Ca is the molar concentration of the acid. Cb is the molar concentration of the base. Va is the volume of the acid. Vb is the volume of the base. Na is the mole ratio of the acid, and Nb is the mole ratio of the base. So for example, in this reaction, the mole ratio of our acid, these are acid, and these are acid, and this is our base. So our Na for this acid becomes equals to M, and our Nb for this acid becomes equals to Q. So you can fix it into this simple formula, and you can get whatever answer, or we can make whatever subject of formula that will be required to get your answer to your question. Now the last aspect of stoichiometry we talk about is the stoichiometry of percentage purity. So it is still an application of stoichiometry. However, what you'll be given in your question will not be a pure substance. It will be an impure substance. Now for every chemical reaction always occurs between two pure substances. The pure substances can be an element or it can be a compound. Chemical reaction typically does not occur between two mixtures or between a mixture and a pure substance. Typically, it is between two pure substances, an element and or a compound. But this time around, we'll be giving an impure substance. Let's say, for example, they will tell you that a piece of razor blade, a certain mass of razor blade, reacted with hydrochloric acid to form a chloride, for example, and I can ask you questions under this area. So that question comes from percentage purity, where we know that in a chemical reaction, it is two pure substances that will always participate in a reaction. But what now happens when we have a mixture? When we have a mixture, it is not the entire mixture that will participate in the reaction. Instead, it will be the pure component of the mixture that will participate in the reaction. So let's assume that I have a certain ore. Let's assume that this is an ore of iron. And this ore of iron contains, let's assume that the ore of this iron, let's say it is equals to 10 grams. 10 grams of an ore of iron contains, out of these 10 grams, let's assume 2 grams is Fe. 2 grams. The rest is impurities. So out of these 10 grams, 2 grams is Fe. Now if I'm to dip this 10 grams of ore into a chemical reaction with an acid, for example, hydrochloric acid, it is the pure component of this ore that will participate in the reaction. And what is the pure component of this ore? It is iron. So if I'm to solve for, if I'm asked to look for the percentage purity of this ore, all I need to do is to determine the mass of iron that will be involved in the reaction. So for example, they can tell me that 10 grams of this ore, 10 grams of this ore reacted with hydrochloric acid. And let's assume if it is to react with hydrochloric acid, we just established that it will be the active component of the ore. So this will be Fe plus HCl to give us FeCl2 plus H2. Look at the reaction. Is the reaction balanced? No. Fixed to here. Does it balance the reaction? There's one Fe on this side, one Fe on this side, two hydrogen on this side, two hydrogen on the other side, two chlorine on this side, two chlorine on the other side. Balance as well. So they can ask us, for instance, we should determine the percentage purity of an ore. Determine the percentage purity of an ore of iron, of 10 grams of iron, if it reacts with hydrochloric acid to liberate, let's say, 4 dm cube. 4 dm cube of hydrogen gas. This time around, we don't know the mass of this ore. We don't know the mass of the iron rather, but they gave us the mass of the ore as 10 grams, and they told us that when it reacted with hydrochloric acid, 4 dm cube of hydrogen gas was liberated. The question is very simple. How? Because we just said that when an impure substance is involved, it is a pure component of the impure substance that will participate in the reaction. So only this Fe here will participate in the reaction. So if I want to determine the percentage of Fe inside this ore, I will first of all need to determine the percentage of Fe that participated in this reaction, which liberated 4 dm cube, because it still be the same amount of Fe that will be inside the ore. So very easy, establish a relationship between what we have and what we are looking for. Our relationship will be between Fe to H2 gas, where this is a mass to volume relationship, and we know what to do from here. So we can simply say 56 grams of iron will always give us 22.4 dm cubes of hydrogen. So what mass of iron would react to liberate 4 dm cube of hydrogen gas? Very easy. So we'll solve. Once we solve, our mass of iron becomes equals to 56 times 4 all over 22.4. This gives us the mass of Fe. So once I have the mass of Fe, which is exactly the same thing as the mass of iron inside this impure substance, I can calculate for the percentage purity. What becomes the percentage purity? Percentage purity is the percentage of the pure substance inside an ore. So it will be equals to the mass of element, in this case iron, all over mass of mixture, in this case ore, times 100. Times 100. This gives me the percentage purity of the ore. They can also ask me for the percentage impurity. So the percentage impurity, I'll just replace the element here with the impure substance. So this place is under this context, it is the mass of the elements, that is the mass of the pure substance divided by the mass of the entire mixture times 100. But if they ask me the percentage purity, I can get it in either of two ways. I can solve for the percentage purity, subtract from 100, or I'll just replace the mass of elements here with the mass of the impurity times 100. I will have the answer to my question. So if I'm asked for percentage impurity, it would be simply be equal to, mass of impurity all over mass of mixture times 100. So that gives me the answer to my question. So if you follow this entire class from the beginning to the end, I believe that every single question that you encounter under stoichiometry, you should be able to provide them with the answers. So if you follow this class from the beginning, I believe that as at the end of this particular class, you should be able to answer every single question that you will encounter on stoichiometry. You can watch the video one more time. If it does not make sense, feel free to ask me questions in the comment section. I'll also respond as well. But please try as much as possible to solve as much questions as you can under stoichiometry based on the fundamental principles of stoichiometry that we have discussed so far. I'll see you in my next class.